Kirk math. All right, here we go. We are on 8.4, looking at quadratic modeling. So we're going to use the quadratic function in standard form to kind of model different situations that might happen in real life. So it's going to be a lot of word problems. Some of these situations you've seen before, like maybe in science or even in math earlier, like how when we framed a picture, here we're going to be framing a pool. Same type of idea, but we're going to look at how to use quadratic functions to model this. And it should be, hopefully, be a second chance to take a look and be a little bit simpler. We're in Student Companion, page 180 to 181. All right. So here we have a company that offers rectangular pool sizes with dimensions as shown. Each pool includes a deck around it. If Carolina wants a 15-foot wide pool with a deck, how many square feet will she need to have available in her yard? So I need the area of the entire pool plus deck so I can figure out if I, or Carolina, wants to put this in my backyard and if it can fit. So we're going to write a quadratic function to represent this area, and you'll see that standard form ends up working out best for this because we are basically just doing a binomial times a binomial. And this is where we have seen it before. So if you remember correctly, we have, oh wait, I'm actually going to just pop right here. So you have your pool dimensions, okay? So everything that is inside this pool is going to be x times 2x. So that is where they get, that would be the inside of the pool. Okay, but we don't just want the inside of the pool, we want to include the deck as well. So I need the area of this entire pool plus deck, okay? There you go. So what I'm going to do, that's how they got this answer right here. Here, actually, let me just make this a little bit bigger for you. Okay, so we're going to just work off of this right now. So that's actually how they got these numbers right here. Okay, is because they took the 2x, which is the length of the pool, and then each of these little lengths here is 4, because we know that from this graphic right here, that the deck is 4 feet on all sides. So if I take the 2x plus the 4 feet plus 4 feet, that's 8 feet, and that's how I'm getting this one right here. And then on this side, again, I know that the width of the pool is x, and again, we're going to add 4 feet on both sides because that's how big the deck is. So this is going to be x plus 8. That's how we got this expression right here. Once I take the length and the width and we multiply it out, we can FOIL it. You can do a box method as a reminder. But you're basically going to do 2x and 8. I do want to go here. Doop, doop. And then this is x and 8, and you're going to multiply together, and that's how they're getting the 2x squared. They have 8x and 16x, and that together is going to make the 24x and then the 64. So then you end up getting 2x squared plus 24x plus 64. Or you could do the FOIL method. I just figured I'd show you the boxes since it's been a while. Okay, but that's how they got this expression right here. So that is my expression. That is the area of the pool, and we're done. That's all I had to do in this particular problem. Okay, so we're using the standard form of the quadratic function to find the area of this rectangular pool plus the surrounding deck. On the next one, we're kind of doing the next thing. We still have the same pool, still the same size, but we want to find the area of the pool and the deck. So if Carolina wants a 15-foot wide pool, so if x is 15 feet, because she wants 15 feet wide, we know the length is going to have to be 2 times 15, so that's 30. And we're going to use our formula here to find the total area of the pool and the deck around it. So what they did was they took their function and they replaced x with 15, right? We did that everywhere. And then they solved, okay? 15 times 15 is where they're getting that number there. which is 225. And then 24 times 15 plus 64. So if I just use my calculator, the first one's 450. 24 times 15 is 360 plus 64. And if I add all that together, you're going to get 874 right there. Okay, so after writing the equation, I can then use the information, plug it into my function, and solve to get an answer of 874 feet squared. That's how much space Carolina would need to build a pool that's 15 feet wide with a deck. Okay. Okay, so now you try, okay? Now you are supposed to figure out, so we're supposed, suppose the pool length in example 1 is now 3 times its width. So instead of 2x, we have 3x as the width. Okay, how does the function that represents the combined area of pool and deck change? So go ahead and write out that function for the pool and the deck. Remember, you're going to end up writing 2 binomials that you're going to multiply together. One for the length and one for the width. And then go ahead and factor that out. Multiply that out, not factor. Multiply that out so that you can get a quadratic function as the area of this pool. And tell me, how does it change? What's different? Okay, so now we have, so that was just looking at area problems, that one right there. We're going to now look at a vertical motion problem. So this is connecting to science. And connecting to anything, the idea in physics, the idea that anything that is thrown vertically is going to have a parabola-like arch to them, because whatever comes up must come down. So even if it is shot really shallow, it's going to arch up and come back down. And so our standard formula here connects really well with vertical motion models, and this is how it happens. So yes, you do need to know this. So I would copy this down, this right here. And we're going to write down what each of these pieces mean, because we need to memorize what they mean here. Above it, really quickly, I'm just going to write the standard form so that you can kind of make that connection. So this is ax squared, bx, and this is c. But in a vertical motion format, instead of x, we use t because we're looking at something over time. And there have these kind of other letters that represent something different we're going to talk about here. Okay, so the variable h represents the height of an object. So the height of the object at a specific given time, that's t, okay, after it's launched into the air, the time after it's launched into the air, is going to be represented by this formula right here. The term v sub 0 is the object's initial vertical velocity. So you can think that b, in my standard formula, is its initial vertical velocity. That's important to know because velocity is telling us how fast something is moving and in what direction, speed and direction. And that letter B is going to tell us that. So if I am given a formula written in standard form, I can just look at the B term and I'll know its initial vertical velocity. Because as you probably know, just from playing around with different things, if I throw something really fast, its arch will be different than if I throw something really slow. Okay, the direction at which I throw it also changes. If I throw it really high up, that will change versus if I throw it really low. Okay, all of these are different velocities, and because it's speed and direction. Okay, so you need to memorize that B is the initial velocity. Okay, the H0 is its initial height. So C is its initial height, but that makes sense because the height is its starting point. So if a frog is jumping, it's obviously going to have an initial height of 0 because it's starting on the ground. Versus if someone is diving, they might have an initial height of 30 because they're standing on a 30-foot diving board. Okay, so it kind of makes sense that's our y-intercept because that is where the y intersects x, which is when x is 0. Okay, when the time is 0, where are we starting? How high up are we standing? Okay, so that's how these two things relate. We're going to do some problems relating these things. And like I said, you need to write down that B is the same as the initial vertical velocity, and C is the same, gives your initial height. Okay, so here's our first problem that we have. We have a diver jumping off of that platform. Okay, it tells us the initial vertical velocity. Hopefully you remember what letter is our initial vertical velocity. Hopefully you said B, because it is. So when I go to write right here, okay, that is going to be 16. Okay, what quadratic function represents the height h of a diver after t seconds after the dive? So first we just have to write our function. And so we know the negative 16 is just automatic there. That's given. It's just always the same for any vertical jump. Okay, we know B is 16 because it gives it to us up here. And then if I go to the diagram, it tells me my C, which is 30. So now I know that C, or H0, is 30 feet. So therefore my function fully written out is h to the t is equal to negative 16t squared plus 16t plus 30. And we're going to use this to solve a problem. Okay, so in our problem, we have our jumper jumping off the diving board, and we want to know how many feet above the platform will the diver be at its highest point. So because this is a parabola, our highest point is also called our vertex. So we're really just trying to find the vertex of this formula written in standard form, okay? And then we're going to figure out the difference between where the man started and his vertex, okay? So I wrote out the standard formula so you can see the comparison. In order to find our vertex or our axis of symmetry, we need to use that fancy formula, negative b divided by 2a. And yes, it's always negative b divided by 2a. So they plugged in the information from the formula up here. B is 16. A is negative 16. They multiplied that out and got 1/2. So that means that it after a half of a second or a minute, whatever time you're using, the man is going to be at his vertex, okay? But I don't want to know the time he's going to be at his vertex. I want to know how high up he's going to be. So I need to find the y value. Okay, so I need to find that y value here when he's here at the axis of symmetry. So we plugged in the 1/2 for t into our original formula, and then they solved that. So 1/2 squared is 1/4. So a fourth of negative 16 is negative 8. Half of 16 is, fourth of negative 16 is negative 4. A half of 16 is 8. 8 plus 30. And when you do the math, you get 34. So the vertex is at 1/2, 34. So that means that at his highest point, he's going to be 34. But when he started, he was 30 feet. So all we have to do is subtract the 2, and we know that he was 4 feet higher than his starting position at his maximum. Okay, so now you guys are going to do the same thing. Here we have a diver's maximum height if he dives from a 20-foot platform instead of 30. And his initial velocity, which is what letter? B, is 8. So write out that formula. Find his maximum height, which is going to be our vertex. And remember to use negative b over 2 times a. And that is it. That's the only examples we're going over. You need to know how to do area with a quadratic function by multiplying two binomials. And you need to know the vertical motion formula, that b is the initial velocity, c is the initial height. And if there is no c in your formula, that means the person standing on the ground. Their initial value is 0. Good luck.